Hi, today we're going to do a couple of additional problems on differentiability and on implicit derivatives for Math 4 honors. So these are some of the more challenging problems, and we're going to start with one that has to do with differentiability. So in problem 1, we're given a piecewise function, a little bit of a complex definition. From x equals 0 to x equals 4, it's defined as 12 minus ax squared. And from 4 to 10, it's defined by k divided by x. It asks us to find the values of a and k that will make the function differentiable at x equals 4, and then it asks us to graph the function to verify the smooth transition from one curve to the next. And I'm going to actually show you how to do that on your graphing calculator. But here we go, let's actually solve the problem. Now, this is a little bit of a tricky problem, because in order for us to be differentiable at x equals 4, we've really got to have two things occur. Number one, we've got to have the graph be continuous there. And that's what we're going to start with. Now, we could invoke the technical limit definition of continuity. But at the end of the day, both of these functions, 12 minus ax squared and k divided by x, are perfectly continuous if x was 4. So what we're going to simply do is set these to equal at x equals 4. So for x equals 4, I'm going to substitute them in. Of course, I'm going to square 4, I'm going to get 16. So I'm going to have 12 minus 16a is equal to k divided by 4. Hopefully you've already discussed this, but if not, all this means is that any values of k and a that satisfy this equation will lead me to have this graph continuous. Just a little bit of visualization there, right? That could mean that we have a graph that, we've got this parabolic quantity. Let me put down 4 here. We got this parabola that starts off at 12, dies down, and then the other thing takes off, right? The k divided by x. So we've now guaranteed that we're going to be continuous as long as this is true. The question is, how do we also make it a smooth transition? And we're going to pull that off by setting the slopes equal. Right? By setting the slopes equal. So for that, what I'm going to do is I'm going to take the derivative of this function. Now keep in mind that both k and a are constants. So the derivative of 12 is 0, and the derivative of negative a times x squared, we're going to take that 2, we're going to bring it down, multiply it by the negative a, and we're going to get negative 2a times x to the first. Alright? I think I'll do this. I'm going to actually leave off the 4 right now. The derivative of k divided by x, if you need to think about that using the power law or the power rule, right? I might think of that as k times x to the negative 1. Bring that negative 1 down, and I'll have negative k times x to the minus 2. And that's going to be from 4 all the way up to 10. Now, in order for the slopes to be equal at 4, we're going to set the slopes equal at 4. In a very rigorous class, we'd say that the slope coming in from the left of 4 is equal to the slope coming in from the right of 4. By setting these two equal, what we're guaranteeing is that the function has no corners at x equals 4, that the transition is smooth. So we're going to do exactly what we did with continuity, except now we're going to set these two slopes equal at x equals 4. I'm going to rewrite this back in its exponent notation without the negatives. Notice we have a negative on both sides of this equation. We could easily multiply both sides by negative 1. That's helpful just to not have to have it sitting there. And we're going to get 8a equals k divided by 16. And I might even simplify that further and just find that k is exactly equal to 16 times 8 times a, which is 128 times a. So as long as my a and my k values satisfy this, we know that the two slopes are equal. But just because the two slopes are equal doesn't mean that we have a smooth transition. In fact, the way that you can have a smooth transition is by having the two slopes equal and by having the two y values equal. But notice that what we now have is a system of two equations with two unknowns, the unknowns being k and a. These are now going to be pretty easy to solve, because what we're going to do with our two equations, let me just rewrite them. 12 minus 16 times a is equal to k divided by 4, and k equals 128 times a. Just going to substitute. All right, that's going to give us 12 minus 16 times a is equal to 128a divided by 4. This will simplify. 12 minus 16 times a is equal to 32a. We can bring the 16a over to this side. We'll have 48a is equal to 12. And if we divide both sides by 48, we'll get a is equal to 12 divided by 48, which simplifies nicely to 1/4. We also want to get the value of k, but that's pretty easy because, as we know from the box above, k is 128 times a. So 128 times 1/4 gives us a k value of 32. So what we now have figured out is that our piecewise function, right, if we substitute in the values of a and k, that f of x equal to, what did we have? We had 12 minus a squared, but we now know what the value, 12 minus a times x squared, but we now know what the value of a is. Right, is going to be that. And we know that k divided by x, where k was 32, is going to apply over this interval. You might think that I'm kind of playing fast and loose with my equality symbols on the 4. Keep in mind, though, by default, because this function is continuous, the output at 4 has to be the same for those two formulas, and you can easily check it. In fact, if I substitute 4 into either one of those formulas, the output would be 8. Now, in order for this to be differentiable, what we should see is we should see a transition at x equals 4 that is both continuous and smooth. Let me show you how to actually do that on your graphing calculator. So, if we have our graphing calculator, let's try that again. If we have our graphing calculator, our TI-84, and I want to graph this, right, I'm going to go into y equals. I'll clear out any equation that's in here. And I'm going to put in the two formulas, but I'm going to put them in y1 and I'm going to put them in y2. So watch what I do. I'm going to do 12 minus 1/4 times x squared. Notice how I enclose that in parentheses. It's a little weird. And then I'm going to put another parentheses, and I'm going to say that x, and I'm going to go into what's called my test menu. That's right above math. X is, what do I want? Less than or equal to 4. Now you might wonder why I don't put the greater than or equal to 0 in there. It's because I'm not going to really be too concerned about what happens at 0 or 10. In y2, I'm going to put my other formula in and put it in parentheses again. Pretty easy. 32 divided by x. Again, close parentheses, open parentheses, x test is greater than choice 3, 4. Alright, now if I've done this correct, what will happen is I'll see that piecewise function graphed. Let's take a look. What do I want my window to be? Let's see. I only want it to really go from 0 to 10. That's good. In terms of my y window, I don't need any negatives. Now you may not realize why that is, but let's just put in, let's say, -2. And I do know that the y-intercept of my function is 12, so maybe I'll make it a bit bigger. Let's go 14. Alright, now let's hit our graph. Isn't that neat? Look at that. You might be bothered a little bit, as many students are, by this sort of vertical line at x equals 4. That's where one formula is taking over. Let me do a little zoom here, show you what exactly is happening. I think I'm going to do zoom box. Zoom box is a little bit harder to pull off, I feel like, on the computer screen than it is on the calculator itself. But for zoom box, I'm going to draw a box around that transition at x equals 4. And we'll see how very, very smooth it is. So there's my box. Well, maybe that didn't look very smooth. But you can tell that there's no corner there, right? It looks very locally linear. And there's no corner there because both the y values match up and the slopes match up. I think I'm going to go back to my old zoom memory, zoom previous. There it is. And it really is kind of neat because that concave down parabola is really kind of going like this. And then that 1 over x type of graph is taking over right there. So we get that smooth transition. All right, let's go on to the next problem. In the next problem, we have a curve that is implicitly defined by the equation y cubed plus x divided by y equals 1/2. Letter A asks us to show that the curve cannot have any horizontal tangent lines. So this is kind of cool. No horizontal tangent lines. Now the tricky thing is I have no idea really what this curve looks like. It's very complicated. It's an implicit function, meaning that if you give me a value of x, I can get a value of y out. But it takes a lot more work to do it, if you can kind of follow what I mean there. But at the end of the day, still, horizontal tangent lines imply one thing. Y prime is 0. And to not have them implies there aren't any places where y prime is 0. So here's how we treat a problem where they ask us to prove that something doesn't happen. We kind of do what's known as a proof by contradiction or an indirect proof. We're going to assume the opposite of what we're trying to prove. We're going to assume that there are horizontal tangent lines and we're going to try to find them. And something along the way, something as we head towards that final goal of finding locations where y prime is 0, something along the way will say to us, this can't happen. All right, but the first thing that we have to do is find y prime, and that's no easy task because we're doing an implicit derivative here, and this is something that a lot of students struggle with. So let's start by writing down our first step in every implicit derivative, which is to take the derivative of both sides of the equation with respect to x. At least at this point, that's the way that we start everyone. All right, remember, derivatives distribute, if you will, not multiply, but they distribute over addition. So the first thing I'm going to do is take the derivative of y cubed. But remember, y is a function of x, so I'll take its derivative with respect to y, that's 3y squared, but then I have to multiply it by y prime, plus. Now I have to take the derivative of x divided by y. I want you to pause the video for a moment, if you need to, and think about what major derivative rule you'll have to use to take the derivative of x divided by y. Did you figure it out? It's the quotient rule. Now pause the video again and see if you can do the quotient rule on x divided by y. Remember, you're taking the derivative with respect to x, so y itself is a function, whereas x is just x. All right, pause the video and see if you can find the derivative of just x divided by y. All right, let's see how it's done. Okay, remember the quotient rule. The quotient rule says take the derivative of the numerator, but that's just 1, times the denominator, y, minus the numerator, that's x, times the derivative of the denominator, but that's y prime, all divided by the denominator squared. So there's our quotient rule. The derivative of 1/2 is, of course, 0. Whew, we have to solve this for y prime. Oh, that looks ugly. I got a y prime here. I have one over here. Then there's stuff without y primes that I need to get on this side. That's not so easy. One thing that's throwing me off a lot is this y squared. What can you do to both sides of the equation to get rid of it? Think for a minute. Did you get it? What I'm going to do is I'm going to take both sides of this equation and I'm going to multiply by y squared. I don't mind doing that to the right-hand side of the equation. It's just equal to 0 there. So what will that leave us? It'll leave us with 3y to the 4th times y prime plus y minus xy prime equals 0. I like that a lot better, right? I can now take this y and I can move it on the other side of the equation. I can gather up all my terms with a y prime and factor them out. I'm going to save a little bit of time here. I think that you're probably at a level of algebraic sophistication that you're going to be okay with that. And then I'll find that y prime is negative y divided by 3y to the fourth minus x. So far so good, and no contradiction yet either, right? I'm trying to show that the curve doesn't have horizontal tangent lines, and I'm going in with the mentality of, let's assume that it does, and find a contradiction. Now, as we're all aware, in order to have horizontal tangent lines, this thing, our beast right here, has to be equal to 0. So let's keep pretending we can find them. We're told that you can't find them, and that we're supposed to prove it, but let's just keep on keeping on. Let's just keep on trying to find those horizontal tangent lines. So we set our derivative equal to 0. But we know that a fraction can only be equal to 0 if the numerator is equal to 0. So that's negative y. Of course, if negative y is equal to 0, then y is equal to 0. All right, great. So this is what we know so far. The only way this thing's going to have horizontal tangent lines is if the y-coordinate on the curve is 0. Fine, whatever. Let's find the x-coordinate on the curve. But in order to find the x-coordinate on the curve where y is 0, we're going to need to substitute y equals 0 into this equation. Okay, again, no big issue there. Let's take y equals 0, and let's substitute it into the equation y cubed plus x divided by y equals 1/2. The only way this thing has got a horizontal tangent line is if I can find a coordinate point that has the horizontal tangent line. So I'm going to substitute a 0 in here and a 0 in here. You probably already see the problem. Right? The problem is coming from the fact that x divided by 0 is undefined. Everything in math has a meaning. Everything can really be clearly stated. And what we can now clearly really understand is that no value of x will ever make this true. Forget about y equals 0. There's no way to take 0 and cube it, which of course is 0. There's no way to take the number 0, add to it x divided by 0, and get 1/2. That cannot happen. And therefore there is no coordinate point, no x comma y, that makes y prime equal to 0. There just isn't any, right? All right, but part B asks us to find the one coordinate point on the curve where the tangent line is vertical. The tangent line is vertical. Well, that's a little bit different. Let's write down the equation for the derivative again. What did we have? We had y prime is equal to negative y divided by, 3y to the fourth minus x. All right, remember, rise divided by run. Right? Rise divided by run. On a vertical tangent line, the run must be equal to 0. So what I know is for me to have a vertical tangent line, 3y to the fourth minus x must be 0. Now a lot of people are very schooled, understandably so, to solve for y. Right, get y alone. But think about that. That would be like, I put the x on the other side, divide by t at 3, take the fourth root. Y would be plus or minus the fourth root of x divided by 3. It's not so pretty, right? Why not just say that x equals 3y to the fourth? Now, keep in mind that that's still not the answer. I'm looking for a coordinate point where the tangent line is vertical, and what I know is that at any coordinate point on this curve, where x is 3y to the fourth, I'm going to have a vertical tangent line. So what I'm going to do is I'm going to take this condition, very nice condition on x and y, and I'm going to take the equation of my curve, which is y cubed plus x divided by y equals 1/2. I'm going to take these two equations and I'm going to combine this. This may actually feel similar to the last problem. Right, here's a condition about the derivative. Here's a condition about the original function. I'm going to take this. I'm just going to substitute it in for x. Look at how nicely it all works out. We have y to the third plus 3y to the fourth divided by y equals 1/2. We can simplify this nicely because a y here cancels a y here and gives us 3y cubed. So clearly we have 4y cubed equals 1/2. I can now solve for y pretty easily by dividing both sides by 4. It may help some of our listeners to instead think about multiplying by 1/4. But now I can take the cubed root of both sides. Remember, the cubed root, unlike the square root, doesn't introduce a plus or minus. Right? And the cubed root of 1/8 upon reflection will be 1/2. There's my y-coordinate of my vertical tangent line. Let's get our x-coordinate. Easiest thing to do is use the fact that at this point, x must be 3y to the fourth, right? X must be 3y to the fourth. So x will be 3 times 1/2 to the fourth. 1/2 to the fourth is 1/16, and times 3 gives me 3/16. So at the end of the day, let me make sure that we don't lose my final answer. At the end of the day, what we can say is that at the coordinate point, 3/16, my computer's having a little bit of an issue there, 1/2. At this coordinate point, 3/16, 1/2, we've got ourselves a vertical tangent line. Alright, that's our discussion on the additional problems for today. Thank you for joining me. Remember, don't get into a staring contest with a llama. They spit. Take care for now. I'll see you soon.